Hello everyone and welcome back. My name is Mr. Kovalt, and in this video I'm going to be going over how to predict electron group geometry and molecular geometry for several molecules. So I'm going to go over some practice problems with you. But before we get into that, in order to predict the electron group geometry and the molecular group or molecular geometry of any central atom in your molecule, you're going to need a VSEPR table, or at least maybe you have it memorized. But you're going to need a table to use. And what I mean by a VSEPR table is some table that shows you the shapes of the molecules or what the names of those shapes are based on the different electron groups around your central atom. Uh, Basically outlining how many total electron groups you have, how many bonding groups, how many non-bonding groups, and things like that. And it'll tell you based on the combination of bonding and non-bonding groups what your molecular group geometry is, and then based on the total electron groups what your electron group geometry is. So remember, just kind of remind you that the distinction between your electron group geometry and your molecular group geometry, or your molecular geometry, is that the electron group geometry is based on the total number of electron groups around your central atom. And that means the bonding along with the non-bonding groups, or your lone pairs. So if you have four bonds, that's four bonding groups. If you have two bonds and two lone pairs, that's still four bonding groups total. So the central molecule that has four bonds, four single bonds, right, versus the central atom that has two single bonds and two lone pairs, they're both going to have the same electron group geometry, because the electron group geometry doesn't care whether or not you have a certain number of bonds and a certain number of lone pairs. It just cares about the total. Whereas molecular geometry cares about how many bonding versus non-bonding groups you have. And so that's why you need the table. So just to kind of show you what I'm talking about here, you would need something like this. Now, it may not be as complicated as this one. Most of them are pretty much like this. And so here you have on the side here, you've got the total electron groups. It says pairs. I don't really like the term pair because, again, if you have a double bond, we treat double bonds and triple bonds as groups, as a single group, although there are in a double bond two pairs of electrons, and in a triple bond there's three pairs of electrons. So I really don't like the term pair in this context. I prefer groups. They use pair because, again, it's in the title of VSEPR. So I think that's something that should be changed or not really used that way, because it could be confusing, and it is confusing, and I've seen the confusion in my students. So I like to say electron groups, not electron pairs. So you have on this table, you have the total electron groups, so 2, 3, 4, and then it divides it up in between bonding groups and non-bonding groups, or lone pairs. And so based on that, you can determine what kind of electron group geometry you have and what kind of molecular geometry you have. And so this is going to be a useful table. So you should have something like this, right? Here's a second page. So you should have something like that to help you with this. So I'm going to be using that and referring to that. So make sure you have that available right now in the video so you can follow along. Okay, let's talk about the electron group geometry and molecular geometry for each of these molecules. So so for this one, we see that this central atom carbon has 1, 2, 3, 4 single bonds. So that's 4 electron groups. So if you look at your table for total electron groups, if you go to 4, And then for the electron group geometry, it should say tetrahedral. So for this one, you have an electron group geometry that is tetrahedral. And again, if you look at the molecular group geometry where you have 4 bonding groups and 0 lone pairs, then your molecular geometry will be identical to the electron group geometry. So as I said before, anytime you have a central atom that has no lone pairs on the central atom, your electron group geometry and your molecular geometry will be identical. So in this case, the molecular geometry is also tetrahedral. Okay, so what about B? We have this molecule here. Notice again, the AS, our central atom, has 3 bonding groups and 1 lone pair. So the total number of electron groups is 4 again. So again, your electron group geometry is based only on the total number. It doesn't matter if you've got 3 bonding groups or and 1 lone pair or 4 bonding groups. So here we have 4, but here we have 3 bonding groups and 1 lone pair. Here we have 4 bonding groups. Both of these have 4, so the electron group geometry is the same. So this is also going to be tetrahedral. Now, because we have a lone pair on the central atom, that indicates that our molecular geometry is not going to be the same as our electron group geometry. So we got to go to our table and look up what would be the molecular geometry in the case if you have 3 bonding groups and 1 lone pair. And when you look at that, you get trigonal pyramidal. So the molecular geometry is trigonal pyramidal or trigonal pyramid. Okay, so here for C, our central atom is carbon, and so we want to find the electron group geometry for that. Now, notice that we have double bonds. Remember, double bonds are treated as 1 electron group, just like single bonds. So this is 1 electron group, and this is 1 electron group. So we have 2 electron groups. Now notice for the double bond, we have 1 pair of electrons and another pair of electrons. So we have 2 pairs, but we treat this as 1 group. That's why I don't like using the word pair. So we have 1 group here, 1 group here. That's a total of 2 electron groups. So for the electron group geometry, we go to our table and we look for the total number of 2 electron groups. And when you see there, you'll see that the electron group geometry is linear. So the electron group geometry is linear. And because we don't have any lone pairs on our central atom, the molecular geometry is linear too. So it's going to be a straight line, 180 degrees. So the molecular group geometry is linear. Okay, next one. We have oxygen as a central atom with 2 fluorines. Notice, okay, what the number of electron groups is. We have 2 bonding groups and 2 non-bonding groups, 2 lone pairs. So again, that's a total of 4. So if we have a total of 4 groups, then what is the electron group geometry? You guessed it, tetrahedral. So the electron group geometry is again tetrahedral. So notice again, here we have 4 bonding groups. It's tetrahedral. Here we have 3 bonding groups and 1 lone pair. That's still 4 total, tetrahedral. Here we have 2 bonding groups and 2 non-bonding groups, 2 lone pairs, still 4, tetrahedral. So the electron group geometry is only dependent on the total number of electron groups. Now, because we've got lone pairs here, the molecular geometry is not going to be identical to the electron group geometry. So when you look on your table, you're going to go to the total number of groups of 4, and then you're going to go over and find the space that says 2 bonding groups, 2 lone pairs, and it should tell you that the molecular geometry of this central atom is bent. Molecular geometry is bent. Okay, so far so good. Let's go to the next 4. So here we have 1, 2, 3 bonding groups. So no lone pairs. So for the electron group geometry, you go to the total electron groups of 3, and there you'll find trigonal planar. So the electron group geometry is trigonal planar. And because there's no lone pairs on the central atom, your molecular geometry is identical. So molecular geometry is also trigonal planar. All right, next, notice we have, again, 1 single bond, 1 single bond, and 1 double bond. The double bond is considered one group. So again, we have 1, 2, 3 groups, just like up here. So this, again, is trigonal planar. And because there's no lone pairs on there, the electron group geometry and the molecular geometry are both the same. So I'm just going to draw an arrow there. So that carbon also has trigonal planar, electron group geometry, trigonal planar, molecular geometry. All right, so for this one, we have more than one central atom. So we have 1, 2, 3 central atoms. So we can identify what the electron group geometry and molecular geometries are going to be. So here we have 1, 2, 3, 4 bonding groups around the carbon, all single bonds, no lone pairs. So again, 4 is going to be tetrahedral, electron group geometry, and molecular geometry. There's no difference. So I'm going to just draw an arrow here since it's the same as A. Here we have a triple bond. That's one group, not 3 groups, one group. And then we have a single bond that's also one group. So for this carbon, we have 2 groups, no lone pairs. So the electron group geometry and the molecular geometry are the same. So that's going to be linear if you look up that on the table. So that's going to be the same as this one here. So I'm going to just draw an arrow there. And again, this has a single bond and a triple bond. So again, two electron groups, no lone pairs. So the electron group geometry and the molecular geometry are going to be linear again. So both of those are going to be linear. And so that's it for that molecule there. And then finally, we have this one. So again, we have 1, 2, 3 bonding groups, 1 lone pair. So that's a total of 4 bonding groups. So the electron group geometry will be tetrahedral. And notice that we have a lone pair. So the electron group geometry and the molecular geometry will not be the same. So when you look up on your table, 4 total 4 total electron groups. 3 of them are bonding. 1 of them is non-bonding or lone pair. When you look that up, you'll find that the molecular geometry will be trigonal pyramidal. And so again, this nitrogen is going to be the same as this molecule here, this arsenic here. And that, ladies and gentlemen, is how you predict the electron group geometry and the molecular group geometry or molecular geometry for your central atoms. I hope this video is helpful. If this really helped you out, if you enjoyed the video, then please like the video, share the video, hit that like button. Also, make sure you subscribe to my channel. When you do, make sure you click that notification bell and click all so you can be notified by all the videos I put out. Finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. If there's a video you would like me to do, any concept you want me to cover, any problem you want me to answer, then please let me know and I will be happy to do that for you. Thanks for joining me and have a great day.